Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class. So today we are going to discuss about the group transfer reactions. So far we have discussed about the transfer or migration of a sigma bond, that is in the name of sigmatropic rearrangement reactions. But now there is a difference between the conventional sigmatropic rearrangement reaction and a group transfer reaction. So in sigmatropic rearrangement also you have seen the migration of a group or an atom from one place to the other place of a molecule. Here also in group transfer reactions, there will be a considerable migration or shifting of the group from one molecule to the other molecule. So if you are very keen on what I am saying, so you can clearly catch up what is the difference between the sigmatropic rearrangement and the group transfer reaction. So group transfer reaction is defined as the transfer of a group or groups from one molecule to the other molecule, via a cyclic concerted transition state. Cyclic transition state in a concerted manner is called as a group transfer reaction, right? So now you can see some common terms which we have been discussing from the beginning of the pericyclic reactions. What is that? So there is a transfer of a group from one place to the other place, right? So but here the places are on different molecules. So initially the group or groups are on one individual reactant molecule transferring completely to a different individual molecule, right? So that is what happening. And next thing is the reaction is processing through a cyclic transition state. So all the pericyclic reactions are happening through a cyclic transition state only. They don't produce any intermediates in the reaction. Okay, and it happens in a concerted manner. Similarly, group transfer reactions are also happening. So what is happening in addition to this means concomitant movement of a sigma bond is also happening. So if you see that the sigma bond is also moving, so you may be confused like, so these are also similar to that of the sigmatropic rearrangement reactions. So in some times, so group transfer reactions will look like the sigmatropic rearrangements. Why? Because here also the migration of sigma bond is seen. Okay. And in some other sense, if you clearly observe it, so two different individual molecules are participating. They are in the cyclic transition state forming a cyclic transition state. That means two molecules are together forming a cyclic transition state, and then one of the pi bond from one of the reactant is transformed into a sigma bond. Where you have seen that type of thing? You have seen that in the case of cycloaddition reactions. So it may also sometimes resemble the cycloaddition reactions. So a group transfer reaction may sometimes look like a sigmatropic rearrangement because a sigma bond is migrating, and then sometimes they also look like the cycloaddition reactions where via a cyclic transition state one of the pi bond is getting transformed into a sigma bond, right? But what is the difference you need to observe here between the group transfer reactions and sigmatropic rearrangements or group transfer reactions and cycloadditions is that sigmatropic reactions are unimolecular in nature. So that means a single molecule will show you the origin of the sigma bond and the termini of the sigma bond, where it is starting and where it is migrating, right? So only single individual molecule is involved in the case of sigmatropic rearrangement reactions. Therefore, they are unimolecular in nature. Whereas group transfer reactions, So, involve two molecules. So, they are not unimolecular, they are bimolecular in nature. So, there ends the thing. So, this is not exactly the sigmatropic rearrangement reactions. And one basic difference we should all observe is a migration or the rearrangement happens within the same molecule. Transfer happens in between two different molecules. For example, if you are sitting here in different places in the classroom, if I ask or request one of the students from the first bench to go back to the different bench, so they are not moving out of the classroom, so they are just rearranging within the classroom. So that is called as rearrangement. At the end of the time, so you can see all the existing students here, that means all the existing atoms will be there, but their arrangement is different when compared to the initial arrangement. So that is called as rearrangement. If I request one of you to go to the different classroom, so what is happening? You are no more in this classroom, no more belonging to this classroom. You have moved to a different classroom. So that is called as transfer reaction. So migration or sigmatropic rearrangement, any rearrangement will happen within the same molecule, whereas transfer happens between two different individuals. So that is why this is unimolecular in nature, this is bimolecular in nature. Though there is a sigma bond migration, and sometimes you feel like group transfer is also similar to that of sigmatropic rearrangement. No, this is not similar. Okay. Next thing is, in group transfer reactions, one of the pi bond is getting converted into a sigma bond. That means you are producing a new sigma bond at the expense of a pi bond, existing pi bond, right? That is what we have seen in the case of cycloadditions. The best known cycloaddition reaction is in between butadiene and this one, ethylene molecule, right? So here what is happening? Via the cyclic transition state, you are able to see a cyclic product. Here in the case of group transfer reactions, though cyclic transition state is observed and then one of the pi bond is getting converted into a sigma bond, you will never see the cyclic product. You cannot see the cyclic product formed between two individuals participating in the group transfer reactions. Okay. So that is the case. So this is also not exactly similar to that of the cycloaddition reactions. So if you look into the simplest example of a group transfer reaction, then by yourself you can judge so whether it is imitating the sigmatropic rearrangements or the cycloadditions, or it is a different other type of reaction. So take a molecule where the transfer of hydrogens is what we are going to discuss now in this example. So what is the primary requirement here you need is this. There should be an unsaturated system, and then there should be two atoms or two groups which are eligible to migrate or transfer from one molecule to the another molecule. So via a cyclic transition state. So what happens is, this attacks here, this sigma bond converts into the pi bond, and then this hydrogen along with this sigma bond will go there. So what is happening? We will get an unsaturated system here, this one, plus what is happening here? Or you are getting this product. So what is the difference here? You can see these hydrogens on the molecule A, and the molecule B is having an unsaturation. Whereas after the reaction, you can see the molecule A with the double bond or unsaturation, and then the groups or atoms migrated to or transferred to molecule B. So this is the simplest example which you can refer for a group transfer reaction. So how it is happening? Via a cyclic transition state. So the hydrogen is there So now this is the cyclic transition state, which is going to give you the conversion like this. So the pi bond which is existing here in the B molecule is slowly moving towards the hydrogen, and the sigma bond is transforming into the pi bond, and then this sigma bond is slowly moving here. So one of the pi bond is getting converted into a sigma bond here. So how many electrons are involved here? 6 electrons are involved. Okay. So a 6 electron involved cyclic, a 6-membered cyclic transition state is seen in the case of group transfer reactions. So now coming into the analysis of group transfer reactions. Analysis of group transfer reactions. So in the analysis of the electrocyclic reactions, or in the case of cycloaddition reactions, we have completely tried to utilize the existing 3 methods. One is the orbital correlation method, and the other is the frontier molecular orbital theory, and then aromaticity method, transition state aromaticity method. Okay. So Woodward and Hoffman, so after exclusively studying these group transfer reactions, has concluded like, so the orbital correlation method or the perturbation method or anything will be used, can be used for the analysis of the group transfer reactions. And again they also said that, so whatever the selection rules they have given for the cycloaddition reactions, the exactly same selection rules will be applicable for the group transfer reactions. So let us quickly start recollecting what are the selection rules according to the Woodward and Hoffman that is used in the case of cycloaddition reactions, and how it is going to be implicated on the group transfer reactions as well. Okay. So now the cycloaddition reactions has been classified into 2 types depending upon the number of electrons involved, right. One is 4n electron system and the other is 4n plus 2 electron system. And if you try to recollect one more important thing in the cycloadditions, if 2 unsaturated systems are adding to each other, then we have to see whether the ends of this unsaturation system are participating from the same phase or from the different phases. If this unsaturated system is utilizing the bond formation from the same phase, it is treated as a supra partner. So if this is also using the same phase, it is also a supra partner. If any one of the unsaturated system is utilizing the opposite phases for the bond formation, then it acts as an antara partner, right. Similarly, we have seen in the case of sigmatropic rearrangements also, if the sigma bond is breaking from one phase of the unsaturated system and migrating to the other end of the unsaturated system in the same phase, we call it as suprafacial sigmatropic rearrangement reaction. If it is changing the phase, then we call it as anterafacial sigmatropic rearrangement reaction. In the cycloadditions, if the unsaturated systems are using the same phase to establish the new sigma bonds, so then they are treated as the supra partners or supra individuals. Similarly, the same concept has to be also used in the case of the group transfer reactions when 2 different individuals are exchanging the groups or transferring the groups. Okay. So the 4n system will have 2 options. One is supra approach, and then other is supra antara approach, right. So you can also take it as antara supra, both are same, and then this as antara approach, right. So in both these cases, under thermal conditions, for 4n electron systems, the symmetry, if you consider as per the orbital correlation method, so you will be seeing like this is forbidden. So supra-supra or antara-antara mode of approach by the individual partners involved in the group transfer reactions under thermal conditions is forbidden, thermally forbidden. So, or symmetrically forbidden. You can also clarify this as they are symmetrically forbidden under thermal conditions. Under photochemical conditions, they are allowed. So, when this is allowed? For a 4n electron system under supra-supra or antara-antara mode of approach. If it is supra-antara or antara-supra, then under thermal conditions, so the reaction is allowed. Under photochemical conditions, it becomes forbidden. So, this is the case with the 4n electron systems, where supra-supra or antara-antara mode is thermally or symmetrically forbidden under thermal conditions and allowed under photochemical conditions. Supra-antara or antara-supra mode of interaction is allowed under thermal conditions and forbidden under photochemical conditions. So, the scenario will completely in an opposite way to that of the 4n electron systems in the case of 4n plus 2 electron systems. So, it also has two modes of approach. One is either both the partners being supra-supra or both the partners being antara-antara. So, they are symmetrically allowed under thermal conditions. Okay. Whereas forbidden under photochemical condition. So, the other mode of approach is one partner being supra and other partner being antara, or the reverse. The first partner being antara and the second partner being supra, whatever may be the approach. So, they are forbidden under thermal conditions in the case of 4n plus 2 electron system, and it is allowed under photochemical conditions. Right. If you recollect it, the Diels-Alder reaction, which is a cycloaddition reaction, you might have seen like on the arrowhead always the symbol representing the thermal condition. So, it is a thermally allowed reaction. So, where this is a 4 pi electron system and this is a 2 pi electron system, together the complete reaction is a 4n plus 2 electron system. So, the 4n plus 2 electron systems are thermally allowed in supra-supra mode or antara-antara mode in the case of cycloaddition reactions. Similarly, in the case of group transfer reactions, you can also see that the 4n plus 2 electron systems are symmetrically allowed under thermal conditions. So, if someone give you an example of this plus this, and on the arrowhead, if there is a symbol representing that this reaction has to happen in the thermal condition. So, what do you feel like here? See how many pi electrons are involved here? So, in this case 0 pi electrons and in this case 4 pi electrons are involved. So, which system it is falling now? In the 4n electron system. So, therefore, under thermal conditions, is the reaction symmetrically allowed? Of course, no, correct, right. So, therefore, the reaction is symmetrically forbidden under thermal conditions is what your answer should be. Whereas, if this is the reaction, so if you see the pi electrons involved here, so this is 0 and then this is 2. So, it comes under the category of 4n plus 2 pi electrons. So, therefore, under thermal conditions, definitely you will be able to see the reaction like this is coming here, this is moving here, and this sigma bond is migrating, transferring there. So, therefore, or you can remove this plus H D or R. So, this will be the product of the sigmatropic rearrangement. Sorry, this will be the product of the group transfer reaction, right. So, the best known example of the concerted group transfer reaction, group in the sense now specifically the hydrogen transfer reaction, okay, is between the diimide. So, what is diimide? So, this one is the diimide system molecule. So, the reaction between diimide and cyclohexene under thermal conditions, right. So, you are going to get nitrogen as the product as well as cyclohexane product. So, now the most important part of this topic, that is the group transfer reaction, is the stereospecificity of the group transfer reactions. So, most of the pericyclic reactions which we have seen are highly stereospecific in nature, and they happen in the concerted manner, and they follow through the process through the cyclic transition state, and most of them are unimolecular and some of them are bimolecular or trimolecular. Okay. So, all these things we have been discussing thoroughly time to time whenever it is required. Okay. Now, coming to the stereochemistry or stereospecificity of the group transfer reactions, always group transfer or hydrogen transfer happens in the syn manner only. So, group transfer or the hydrogen transfer happens in the syn manner. That means same side, both the atoms or groups will move to the same side of the unsaturated system. So, for example, take the diimide again, which is deuterated now. So, this is diimide. So, diimide upon reaction with a malic acid. So, what is malic acid? This one, cis dicarboxylic acid. Okay. So, what should happen means both the deuterium in the place of hydrogen, already you have hydrogen here. So, that is why we have converted this into dideuteriodiimide. So, both these deuterium should add in a syn manner. This is malic acid. So, under thermal conditions, what is happening? It is adding in the syn manner. N2 you will get as the product, and now COOH, COOH and D in the same side and H in the same side. So, you will be getting a meso product in the case of a cis reactant. This is cis compound. No. So, why this is happening with the cis compound is the addition or the transfer is in the syn manner. So, syn manner of group transfer. What is the group here transferring? Deuterium. So, if it is fumaric acid, which is the trans molecule COOH. So, then what is going to happen? The similar is the thing you can observe anywhere. Okay. So, you will get D. So, they are on the same side. So, now the question is, what about the carboxylic groups? So you can see them like this. So you will get DL mixture. Okay. So if it is the trans product, you will be getting DL mixture. If it is the cis product, cis reactant, you will be getting a meso product. So in any case, whether the reactant is in cis configuration or in the trans configuration, one thing is for sure in the case of group transfer reactions, that is syn transfer only takes place. In the syn manner only, you will be transferring the atoms or groups. So that means these two deuteriums are cis to each other. Here also these two deuteriums are cis to each other, same side. Okay. So this thing you have to keep in mind. So always whatever may be the configuration of the reactant molecule, unsaturated system, here in this case the malic acid which is cis and fumaric acid which is trans, or if you take diols or if there is a phenyl group, whatever may be the case, if you take the cis molecule or trans molecule, the addition or the transfer takes place in the syn manner only. So not only olefin, if you take substituted acetylene with diimide, so this is diphenyl acetylene. So what will happen here again? Under thermal conditions, because group transfer reactions are thermal reactions, so you will be able to see nitrogen plus, so you will get cis molecule only. So the speciality of the diimide molecule in reducing the system, unsaturated system, is that so it is highly chemoselective, stereospecific in nature, chemoselective in nature. Okay. And it does not demand any harsh conditions. So under milder conditions itself, the reduction can be easily done using the diimide molecule and you will be getting a product. Okay. So if you see this example where you can see different types of unsaturation and reactive parts of the molecule. So what we can see is this portion is highly reactive and there is one unsaturated system, carbonyl system, and this double bond is highly substituted double bond, and this is also one more double bond. Under these conditions, if we use diimide, which is a highly stereoselective or chemoselective reagent, what happens is here it has three options to react, but it will choose to react at this place only. So it will not touch the epoxide, it will not touch the carbonyl function, and it will not touch the high substituted unsaturation. It will do the reduction at this portion only. So diimide is highly chemoselective and stereospecific in nature. So if you have dihydronaphthalene, hydrogen here and cyclohexene. So what happens is it easily converts into naphthalene plus you will get the cyclohexane molecule. Okay. And if you have this anthracene, so this is the anthracene. So with anthracene, if you use a reagent which can give the hydrogens, so you will be having some confusion where these two hydrogens will be transferring, where the reduction will take place. So the highly reactive position for the anthracene is here. So after the transfer of hydrogen, this particular ring at the center might lose the aromaticity, but that is not a big problem. because the center ring has smaller stabilization energy as compared to that of the benzene. So that is why, so the hydrogenation or reduction takes place at these positions, as a result of which you can see the product. Because the hydrogen has transferred, this is happening, right? So you will also get to see benzene, this one. So there are some more examples in this category. You can always try and work out. So if any doubts, we can discuss later. So this is all about the group transfer reactions. Thank you.